Welcome back. Today, we're going to jump into a super common algebra question, how to find a graph's domain and range. We're going to figure out the entire story of this function just by using the visual cues right in front of us.
So I want you to think of yourself as a visual detective. This curve here, it isn't just a random line. It's a bunch of clues telling a story. And our job is to figure out what this function is allowed to do. And, just as importantly, what it isn't.
You see, every graph has a secret story, a set of rules and boundaries that it has to live by. Our job is to uncover them, and to do that, we're going to need our detective's toolkit. And here they are, our two most important tools, domain and range. These two concepts are basically the secret keys to unlocking any graph story. So let's break down what they actually mean. Okay, this chart lays it out perfectly. The domain is all about the inputs, the x values. Think of it as all the numbers you're allowed to plug into the function. The range, on the other hand, is all about the outputs, the y values you get back. The simplest way to remember it, domain is horizontal, left to right. Range is vertical, up and down. Here's a really cool way to think about it. Imagine a giant light shining straight down from the ceiling. The shadow that this graph casts onto the floor, onto that x-axis, well, that's your domain. It's the total horizontal space that the graph takes up. All right, detective, it's time to get to work. Let's start by scanning left to right all along that x-axis. We're on the hunt for any clues about the graph's horizontal limits.
Take a really close look. There's one specific thing on this graph that's practically screaming, "Hey, I'm a boundary." Do you see it? Yep, it's that vertical dotted line. That is our single most important clue for finding the domain.
Now, that dotted line has a special name. It's a vertical asymptote. The best way to think about it is like an invisible electric fence. The graph will get closer and closer and closer to it forever, but it will never ever touch it or cross it. It's a hard boundary, usually because that specific x value would make the math impossible, like trying to divide by 0. And this makes it crystal clear where our invisible fence is. The asymptote is that vertical line where every single point on it has an x value of 2. This is the forbidden zone. So the big rule for our function is simple. Its x value can get crazy close to 2, but it can never, ever actually be 2.
So the whole process is actually pretty simple. Step 1, you focus only on the horizontal x-axis. Step 2, you find that do not cross line, which for us is at x equals 2. And finally, step 3, you just describe all the x values where the graph is actually allowed to exist.
And that leads us right to the answer. Since the graph can't touch x equals 2, but it stretches out to the right forever and ever, the domain is simply all the numbers that are greater than 2. The key thing here is that the number 2 itself is not included. Now in math, you'll see this written in two common ways. First, there's inequality notation, which is just x is greater than 2. Then there's interval notation. That round parenthesis next to the 2 is really important. It specifically means not including 2. And of course, the infinity symbol means it goes on forever. Both of these are totally correct ways to write the answer. All right, half the case is solved. We've totally mapped out the horizontal footprint. So now, let's switch gears and investigate the vertical reach. It's time to find the range. So for the range, we're going to flip our perspective. Instead of that shadow from above, I want you to imagine we're squashing the graph from both sides, pressing it flat right onto the y-axis. What parts of that vertical axis would get covered in ink? Let's look at what the graph is doing vertically. As it goes to the right, it's climbing up, slowly, but forever. And as it gets closer to that asymptote, it just plummets downward forever. So are there any horizontal barriers? Any ceiling or floor? It really doesn't look like it. Exactly. Since the graph goes up forever and it goes down forever, it's eventually going to cover every single possible y value there is. There are no vertical limits at all. So we say the range is all real numbers. And the interval notation for all real numbers is just beautiful and simple. It's from negative infinity to positive infinity, telling us the graph's vertical reach is totally limitless. And there you have it. Case closed. We cracked the code. The domain, which is our set of all allowed inputs, is everything greater than 2. And the range, our set of all possible outputs, is all real numbers. So you might be thinking, okay, that's a cool puzzle, but why does this actually matter? Well, understanding a function's limits isn't just some random classroom exercise, it's a really foundational skill in math. Seriously, you are going to see this concept everywhere. It's a huge deal in algebra, it gets even more important in pre-calculus, and you'll almost certainly see it on standardized tests. But more than that, it helps you understand the boundaries and limitations of real-world problems that are modeled by functions. And hey, don't just take my word for it. The source material for this whole explainer hammers this home, calling it a very important skill. This isn't just some trivial problem. It's something you are definitely going to see again as you keep going in math. So we started out with just a mysterious curve on a page, and we ended up reading its entire story. And the key was just knowing which clues to look for. It really makes you wonder, right? Now that you can find the hidden rules in a graph, what other secrets is math just waiting to reveal?